Hello physics students, welcome to your second video on the introduction and revision section, and we're continuing with our motion in a straight line section. Let's do an example. We're talking about acceleration, and we recognize that over here in our formulas we have acceleration in a number of formulas. This one here is one we would use quite often because acceleration equals the change in velocity divided by the time period it takes. And so the change in velocity is v minus u and the time is t, and we can take this and rearrange it to this. So you have this formula here already on your information sheet. And in this case, let's look at this example. Some Americans did some experiments and revealed that the beak of the red-headed woodpecker hits the bark of a tree at an impact velocity of 5.8 meters per second minus 1 and comes to rest in 0.059 seconds. Calculate the deceleration of the bird's head. And as per usual, when we do these sorts of questions, hopefully what you're doing these days is circling the information that you know, exactly as we did in physics before. Let's move that piece of paper out of the way, and we go on to this. And so our piece of information, there's our impact velocity, comes to rest, alright, and there's that. So that's going to be u, that's going to be v, and that's going to be t, and we're after a. So helps when you identify the numbers that you're given, assign the corresponding letters to them, and then you can work out the formula. Okay, all this other stuff is noise that makes the question interesting or not, depending on what sort of mood you're in, but it's just there to confuse you a little bit, I guess. So let's have a look. So we're going to use this formula here. We put our numbers in and we do the maths, and we get 98.3 meters per second to the minus 2, which is approximately 10 G's, where 10 times the gravitational force that you experience. That's quite a deceleration. Now, instantaneous velocity. Instantaneous velocity is when you have something changing its velocity, and we just want to look at a snapshot. And here we have just a graph. It doesn't tell us what it is, but it's time versus position. So effectively it's a displacement time graph, and we know that the slope on a displacement time graph gives us the velocity, but the slope is constantly changing. So if we wanted to work out an instantaneous velocity, for example here at about 2.5, we draw a tangent to that slope, and then we work out the slope of the tangent. A bit complicated. And so in this case it would be, what's that, 2.5 would be the run, and the rise is about 22, and we could work out the instantaneous velocity. Obviously, if we, let's pull up my pencil again, if we drew another tangent, now this is a bit dodgy, if we drew another tangent here, hey, that's not too bad, we would notice that the slope is greater and therefore the velocity is greater. And if we did a slope down, a tangent down here for this point here, we notice that the slope is again reduced. So in this case the velocity is increasing because the slope of the tangent's increasing, and we can say it's accelerating. Right, let's get rid of all that. Let's get the magic mouse up again, and let's click. Alright, so changing velocity equals acceleration. Now, motion graphs, here's another one, time versus displacement. What does this graph say to you? Alright, have a look at it. Pause the video, think about what you're going to say or think. What does it mean to you? Okay, my interpretation of it is, okay, because it's a displacement time graph, anywhere that's a slope gives us a velocity. Anywhere where there's no slope, it means it's stationary. So we have stationary there and stationary there. We have it moving with a constant velocity there. We have it moving with a constant velocity there. But notice that these slopes are not the same, and therefore those velocities are not the same. And here we have a negative slope, so it has a negative velocity. And to assist me working all that out, I would draw my little rise over run, or fall in this case, and work out my slopes. And then I could say a lot about this graph. Okay, and it looks like, well, it doesn't look like this. This is another graph. So we're not going to actually work things out unless we have to. So here we have a velocity time graph. Remember, a velocity time graph, what does the slope tell us? Well, also remember that whenever you get a graph, look at the axes, work out what sort of graph you're looking at. And this one being a displacement time graph, the slope gives you the velocity. This one being a velocity time graph, the slope gives you the acceleration, and the area under gives you the displacement. So, what would the acceleration time graph for this one look like? You'd have to actually work out the slopes by working out the rise over run, and you've got a negative acceleration there, so deceleration. What does it actually look like? Here we go, that arrow is pointing to this. Whoa, it should look like that. So you had a period of positive acceleration, then a period of no acceleration, still travelling at a constant velocity though, and then a period of negative acceleration or deceleration. Right, that's it. That was short and sweet, wasn't it? Trying to break it up into bite-sized pieces for you this year. So in the next video we'll continue on with our revision. So cheerio.